Hey. E ngā mana, e ngā hau, e whā, tēnā koutou katoa. Nau mai haere mai, e koa ana te nākau kua tau mai koutou. Ke te whakanui e te kaupapa o te rā. Nō reira e aku rangatira. Tēnā koutou, tēnā koutou, tēnā koutou katoa. I'm Professor Merrin Tawhai, Director of the Auckland Bioengineering Institute. This is Professor Piers Kelly, Head of the Department of Engineering, Science and Biomedical Engineering. It is with much pleasure that we welcome family, friends and colleagues to this inaugural lecture to recognise Justin's promotion to Professor. We've both known Justin in various capacities for more than 20 years. First as an undergraduate student in the department and then as a PhD student. We studied together at the same time, we overlapped. And he was supervised by distinguished Professor Peter Hunter and by Piers. Justin graduated with his PhD in 2004, for which he was awarded a Vice-Chancellor's Prize for Best Doctoral Thesis. He immediately took up a Research Fellow position at the University of Melbourne on an Australian Research Council postdoctoral fellowship, and he then secured a position as a research scientist with the Australian CSIRO. We were fortunate that he returned to ABI in 2010, soon after which he was awarded one of the inaugural Aotearoa postdoctoral fellowships. He subsequently secured a joint teaching appointment with the Department of Engineering Science, as it was then. Justin has contributed to ABI leadership as Associate Director Postgraduate. He holds an adjunct appointment with Ningbo University in China and has had a long-standing relationship with universities in the Philippines. Justin exemplifies the ABI values of excellence, collaboration, collegiality and curiosity. He's had considerable success securing Marsden, HRC and MB funding, is co-founder of Formus Labs. He is an excellent PhD supervisor and is incredibly productive. But despite how busy he obviously is, every time that I see Justin, he has a smile and maintains positive energy. Justin has turned his attention to diverse research topics. He's not scared to give something new a go. I took a quick look at his Google Scholar page and I saw knee joint kinematics, shod and unshod runners, and wet industrial banana screens. So this evening's inaugural lecture promises to be interesting. Nō reira, tēnā koutou katoa.
Thank you, Merrin, and tēnā koutou katoa. I'm Piers Kelly, I'm the Head of the Department of Engineering Science and Biomedical Engineering. And as Merrin said, Justin has his foot in two parts of the university, one in the Auckland Bioengineering Institute and one in the department. So I'm going to spend a little time talking about his time in the department. As Merrin said, Justin was actually an undergraduate in the department. He did his final year honours research project with Dr. Murray Smith on the variability of the marinade injection for Tegel chickens. It's a pretty interesting start to his research career. He also won the prestigious Senior Prize in Engineering Science at that time. So he completed his PhD with Peter on the contact mechanics of the knee, just when the Auckland Bioengineering Institute was being set up. And after his time away, he returned to the department to take up his senior lectureship in 2013. So over the course of the following 10 years, Justin has had a great impact on the workings and performance of the department. And first off, he's a leader in research-led teaching in engineering design, mathematical modelling, and biomedical engineering. He's been heavily involved in curriculum restructurings and the development of key departmental courses. And one of these courses he was instrumental in setting up was musculoskeletal and orthopedic biomechanics paper, which very typically of Justin's teaching is a great vehicle for translating his current research into teaching practice. And I mentioned this paper in particular also because it is invariably the top rated student ratings paper of all the 40 papers that we deliver in the department each year. So testament to generally very high quality of Justin's teaching. Justin's teaching has also been recognised overseas through invitations to present internationally. He's given lecture series on muscular biomechanics to researchers from all around Europe, and he's also given multiple short courses and workshops to students and researchers in engineering, sports science, and medicine. Justin has supervised a large number of PhD students and master's students, and in our department he's supervised well over 30 undergraduate students in their final year research projects. And I think his passion for supervision and postgraduate experience led him on to take these roles of department graduate advisor about 6 years ago. And essentially, this role, you look after all the postgraduate issues in the department. And these kinds of university positions, they've got a lot of roles and responsibilities associated with them. But I'm just listing them wouldn't do justice to what Justin has done with that. I'll just mention two of the things he's done over and above. He's led a very arduous 2-year process getting the development of a new cross-department Master of Medical Engineering, and this is the only taught biomedical engineering program in New Zealand. And more recently, Justin has been leading the cross-faculty of Science and Engineering shared Master's program, which will run between our department and the Department of Math at the University of Auckland and Northeastern University of Tsinghua in China. Justin has also taken up other important leadership positions. He's an integral member of the department executive, was a key person in the recent Engineering New Zealand accreditation of the department, and also the implementation of the university's curriculum framework transformation. Justin also serves as an elected member of the university's international committee. Okay, so finally I'd like to mention one last thing, one other contribution Justin's made to the department over the years. So just to explain this, we get our second year students come into our department after a general first year engineering, and we bring them on a field trip. So we take about 100 students and about 3 or 4 staff, accompany them down to visit companies, carry out events, and so on. And it's a huge commitment, and Justin's been the organizer for this and attendee for 7 or 8 years. So it's a big commitment. But I also want to tell a little story about this. We usually end up in Taupo and Rotorua on the final day, and the students are racing around the city, or the town, and they're trying to win this amazing race, kind of treasure hunt thing. And the staff, meanwhile, are trying to get a piece of quiet. They sit in a cafe out on the street having a nice time. So one of the things that students invariably need to do is they've got to tick off on a little sheet. They've got to say they've stopped someone on the street and they've challenged them to an arm wrestle. So students running around the town, they invariably see the staff members and they come over to the table and think, well, this is going to be an easy one. Let's go up and challenge these people. And the staff say, no, I don't think it's a good idea. Well, maybe we could try Justin. So the young gun goes up to Justin, and little do they know that Justin has been studying the biomechanics of the arm for 2 years, 10 years, and he proceeds to crush these poor innocent students. So it's a good introduction to the department for them. But really, Justin's attendance at these field trips is indicative of what Justin brings to our department at the university. He brings a huge passion and energy for tertiary education and research, for the student experience, and also doing a lot of unseen, high-quality work behind the scenes too. So it's a real credit to the faculty and the university. So I'll stop there, and so let me please introduce to you Professor Justin Fernandez.
Thank you, Pierce and Maren, for those very kind words. What you don't know is that there was weeks of physiotherapy involved afterwards when I arm wrestled those students. I don't tell you about that. Tēnā koutou katoa, no Australia aho. Engari, kuaroa te wā o e noho ki tēnei, whenua o Aotearoa, ki Tamaki Makaurau, koinei toku kainga. E kainga ko o te mahitahi ki te taha o aku whānau, core engineering, core ABI, rātou core matai. tēnā koutou, kua whai wahi, moku te haramai, ki te whakawhiti, whakaaro, me te kōrero. So, even though I'm originally from across the ditch, New Zealand has been my home for a very long time. I've spent more than half my life here. So often when people ask me where I'm from, it's probably somewhere in the middle of the ditch. But in that time here, I've definitely come to treasure my engineering, my ABI, and my Matai research families. And I just want to thank everyone for giving me this space today to share my stories and to share my experiences with you. But what I really wanted to talk about today was some of those unexpected adventures that I had, things that I never thought I would get involved with. And I actually looked at all the topics and I picked out some that I thought were quite interesting, and I tried to create a Dr. Seuss rhyme. And basically I picked out the word screws and shoes and clues, and I threw them into an AI image generator. And this is what I got. And I had a lot of fun with it, and I was very curious about the last one. This is what it thought, basically on your right there, that it thought about ADHD and MRIs, basically a Dr. Seuss in the brain. So as you can see, I had a lot of fun with my title page, probably a little too much fun. Those AI image generators are real time wasters. Okay, let me just turn this on. So before I begin, I just wanted to acknowledge people that have been very important to me in my life and in my career. My parents, Philip and Denise, some of you met them this evening, and I'm very happy that they could come across the ditch and join me this evening. They've always encouraged my curiosities and let me go my own way, and I thank you very much for that. But somehow, they managed to turn this crafty little fellow into someone slightly useful in society. My sisters, Kimberly and Chandel, and my brother Nathan, always up for a witty debate and critical discussion, especially about my areas of research. I often feel like it's a second peer review. And I've got a whole bunch of nieces and nephews. Actually, 2 more have been added to the group. And when I look at them, I think about the future of our family. I really do hope that at least one of them becomes an engineer. Maybe I just have to keep showing them cool stuff. My partner, Jen, been with me for many years. She always provides a very balanced ear, especially when I don't get my grants. But she's always showing me new experiences, and I look forward to many more adventures with her. And my student partner. Without these talented individuals, none of my ideas or ambitions would ever come to fruition. So I actually tried to find photos of them all. I realized over the years there's close to 29 PhD students now. And what I did find was some photos of some of the good times we had at conferences and also after thesis defense. I also noticed that we always seem to be eating and drinking, which may in part explain my changing shape over the years. And there's my academic colleagues. Whether I've researched with you, taught with you, been supervised by you, or mentored by you, I absolutely value the contribution that you've made to my career. So thank you. So, where did my unexpected venture begin? It actually began by ticking the wrong box on a form. That's correct. I ticked the wrong box in a form. And in the summer of '99, I just finished MSci. And I was very fortunate to meet Peter and Pierce. And I was very keen on doing a master's degree. And at the time, of course, Peter was founding the early days of what we know the ABI as. It was called the Bioengineering Institute at the time. And I actually found this photo on the inside of my thesis. And you can see it was a very tight-knit group. And I actually looked and I realized that, as Miriam pointed out, we kind of overlapped. She just finished her PhD, I think, here, was a research fellow. And right beside her was Nick Smith, who we all know was one of our former deans. A very tight-knit group. We all used to be on one level. And Peter encouraged me to apply for a scholarship. At the time, it was known as the Foundation for Research, Science and Technology, for those of you who remember that. And as a student, as you do it on the last day, and I was running around getting signatures and transcripts photocopied, and in a rush, I ticked the box that had the most amount of money in it. Turns out that that was a PhD scholarship, not the master's. So fast forward a few months, and I was very fortunate to get the scholarship, and Peter kind of encouraged me to stay on. But it was actually the ambition that my supervisors had at the time. And essentially, what we wanted to do was take all these tools and technologies that you develop for the heart, for the lungs, for the gastrointestinal system, and apply them to the musculoskeletal system. And I really have to acknowledge Richard Christie at the time, who really helped me a lot with all the visualization and graphics and the development of a package called C and GUI that we often use. And Kumar, who helped me build a lot of these geometries. At the time, believe it or not, the ABI had its own MRI machine. We used to have a lot of fun playing around on that, and I used to invite a lot of people in, and while they slept, I would image their knees. But around midway, I realized that I'd overcommitted myself, and so I downsized to just focus on the knee joint. Okay, and so this was a bit of a correction that I made. I realized there was a lot of interaction between these structures that I had to solve. So I spent almost a year implementing what we call contact mechanics. And as reality would have it, by the time I submitted my thesis, it was just one bone, the patella. So this is a really good example when I look back on how a student's enthusiasm gets curbed throughout their PhD. But it turns out it was a really good bone to do. And just recently, when doing some orthopedic simulations with Hall and Tor, a couple of my colleagues in orthopedics, we came across a couple of interesting observations. Well, first of all, for those of you who have never seen a knee joint replacement, this little plastic button up the top there is what replaces your patella in an implant, rather simplified compared to the anatomical structures of the patella. And what we were doing when we were simulating it was trying to get an understanding of the wear in an implant. But we realized that when we were simulating it, the patella was translating in the complete opposite direction to it does in the natural knee. And no one could explain it to us. So when you actually flex your knee, your patellas actually slide outwards and laterally, but in an implant, it was doing the complete opposite. And so we still haven't got an answer from a lot of the orthopedic companies. But what we did do was we actually took an implant, and as you can see here, it's sliding, as it slides down, it slides slightly laterally. We actually redesigned the implant based on a population of shapes and slightly corrected it so that when it slides now, it actually moves more like the natural knee. So a subtle adjustment, and we really got the orthopedic companies interested in that one. But I did this for 4 years. Simulation, modeling, spending hours coding in Fortran, one of the best languages. And I decided at that point that I think I'd like to learn some more experimental techniques. So I jumped across the ditch and I joined the lab of Professor Marcus Pandy. And in that lab, this was my first group of colleagues. And the guy with the arrow over his head, the gentleman, was my very first PhD student too. Masood. And the problem that we were trying to solve was the one using motion capture. So those of you who know about motion capture, essentially motion capture is used for animation or sports biomechanics. And what you do is you put these little markers on your skin. And those markers are supposed to represent the underlying skeletal motion. And then if you combine that with some force information, you can actually work out the loading at your joints and ultimately an estimate of your muscle forces. The problem is, if you look at an X-ray fluoroscopy machine, you see that little marker there. That's actually a marker on your skin, and you can see how much it's actually moving relative to your bones. It's actually in the order of centimeters. So that error is propagated all the way through your workflow, and it causes problems and errors in your calculations. So what we were trying to do, and there was only a few groups around the world that were trying it, but we set up the very first one in this part of the world, was to use an X-ray fluoroscopy machine in a gait lab to try and get accurate joint motion. And they're actually available in hospitals. They actually look like this. They're called C-arms. And they actually go around your bed. But we were trying to dismantle it and connect it up with motion analysis equipment. And what you did was you built these three-dimensional models using either MRI or CT, and then you took these two-dimensional X-ray images. Okay? And then you used a technique known as perspective projection. And the best way to think about this is if you held up this three-dimensional knee and you shined a torchlight on it, the 2D silhouette that it would make on the wall is like a 2D projection. And you would keep changing this position until basically this 2D projection matched what you saw in the X-ray. And you would do that for every single frame. And if you did it enough, you end up with very accurate three-dimensional kinematics of orders of error less than a millimeter in translation and less than a degree in rotation. So we were very successful at doing this. We often followed people during their rehabilitation programs. We were looking at people who had joint replacements in orthopedics. But the question we always got from everyone was, this is all good, but how much ionizing radiation am I being exposed to here? And so our patients were worried. In fact, my student and I were a little concerned too, because we were exposed all the time. So we brought in a radiation physicist to say, can you tell us how much radiation you're likely to experience from one of these sessions? And he did the calculations, and he told us it was so low that you were more likely to get a higher amount of radiation if you took a flight from this part of the world to London and back again. Being at that altitude, you get more radiation. So I was quietly happy at the time, but I also was starting to think about all those conferences I was attending and how much radiation I may be getting from that. But this is actually how we used it. Okay, so we were doing experiments where you would do a task, you would get the accurate X-ray fluoroscopic information, you would get these three-dimensional models, you would get force information, and you combine them all together in a computer model where we could measure personalized bone stress. And we use this in rehabilitation, we use this in orthopedics, and I have a lot of fond memories of this set of stairs over here because I don't know how many of you can ever remember the very first research grant you ever got. But when I was at Melbourne Uni, I got a Melbourne University Early Career Research Award for $10,000. I clearly remember, I was so overjoyed. And I used more than half of that money to design and build these stairs. So we designed them, we took them to a staircase maker, who was also very interested that they were asked to make this. And you can move the stairs around and replace the force plates. And recently, when I visited the lab, I was very happy to see that they were still in action and still in use all these years later. So that was a well worth investment. Now, at that point, I wasn't sure I wanted to be an academic. In fact, I just wanted to be an engineer solving cool stuff in industry. And so I actually decided to join Australia's largest science agency, the CSIRO. It's kind of like one of New Zealand's crown research institutes. And this group that I joined used particle mechanics to solve a lot of industry-based problems in minerals and mining. And I was so excited when I joined this group and I found out that my boss at the time, Paul Cleary, was not only one of the leaders in the field of a method known as SPH, or smooth particle hydrodynamics, but he did his PhD with the professor who invented the method in the 70s. So Joe Monahan, professor of maths at Monash, was actually his PhD supervisor. So I was so excited that I felt like I was just 2 degrees of freedom away from the guy who invented the method. And I still tell my students today when I teach them in class and I'm teaching them SPH that they're just 3 degrees of freedom away from the guy who invented the method. But what we often did was we use these particle simulations, and they're kind of like numerical experiments, to solve various problems. And even though a lot of the stuff I did was commercially sensitive, there were some things that I did that were research-based and published, so I can kind of show you. And this problem was a problem involving hoppers or silos that are often used to store food. And the problem that they were having was some of the food was coming out and it was a bit degraded, or it was lower in quality, or sometimes it never made it its way out. And what we used to do was run these simulations where we would color these particles so we could see where they're actually coming from. And what you have on the left-hand side here is your classic screw that they were using, and on the right-hand side is a new screw that we designed to hopefully fix the problem. So what happens is when you start to draw down this material, it all comes down from the rear, and all this material at the front really starts to stagnate and stays there for a long time. And if you keep topping that up, this material at the front never makes its way out. And this is the problem that they were having. So what we ended up doing was we designed this new screw that was tapered and it had increasing volume. And the problem with this is that as the material was moving along, it had no more volume to introduce new material into the screw. So with our new design, we were able to, basically kind of address the problem. So the material came down more uniformly. And so that was a very good model, and it was actually used later on to inform the people who designed these hoppers and silos that maybe they need to use our kind of designs of screws. So that was a really cool problem. And the other problem that I looked at was Brazil nuts and banana screens. Kind of sounds like a fusion dish. But I worked on this with Paul Cleary and Matt Sinnott, and a good way of thinking about this is, have you ever bought a jar of nuts from the store, mixed nuts, and you always find that the big nuts sit at the top for some reason? Okay. This is due to a physics effect known as the Brazil nut effect. And I actually use the simulation here that I teach students in classes to where it comes from. So as you can see, you've got big particles at the bottom, and if you happen to shake it at just the right amplitude and vibration, these particles will start to make their way to the top. And it's because all the voids at the bottom are filled by the finer particles, and because of circulation and contact, these larger particles kind of make their way to the top. Well, that Brazil nut effect is what they use in the mining and minerals industry to try and separate particles out. And so on the right there, you have what is called a banana screen. So essentially what happens is you get minerals and ores, they come down from the top, and they have all shapes and sizes, and they vibrate these banana screens using this Brazil nut effect knowledge, and the larger particles make their way to the top, the finer particles end up in the bottom, and then they filter through the grate, and you're able to separate out all these particles. And if you get it just right, you can get most of the separation done in only 1 or 2 passes. So, this interesting effect, the Brazil nut effect, if you get it right, you can actually make processing and separation really efficient in these industries. Now, I remember when I came to the end of this, I was really enjoying all the problems that I was solving, but I kind of missed the interaction with students that I had at Melbourne Uni, and I kind of missed a lot of the teaching that I used to do. You don't really get that when you work at one of these science agencies. So I remember liaising with Peter about that time, and I said to Peter, I'm kind of interested in coming back. And I can remember Peter telling me, he said, that's great news, Justin. And I have some other good news too. I've just been talking with Tor Bezier at Stanford, and I think he's keen on coming back too. So I was really excited because here's this other guy that I've been working with for years, but at other ends of the earth, and there's a chance that we might be back at the same institution. So I came back to Auckland University. And one of the first projects that I actually got involved with used a lot of that knowledge on particle mechanics in a very interesting application in the field of forensics. And this was a really nice collaboration between ABI and MSci and Mechanical, which then was had the Centre for Advanced Composite Materials, and ESR, which is one of our Crown Research Institutes. And this work, which was led by Aaron, was concerned with a particular problem in crime scene investigations known as the backspatter effect. Okay? So I won't go into any of the morbid details, but when a projectile basically enters an object, while most of the fluid goes in the forward direction, some of it goes in the reverse direction. And that can actually tell police, they can actually tell forensic scientists something about that scenario. So we were trying to better understand that and also to turn it into simulations. And Aaron had an absolute ball down in Newmarket, 3D printing and moulding heads, choosing different simulant materials. We even had a gas gun, and we also had a high-speed camera to capture these effects. And what we were trying to do was build models that were validated by these physical models. So on the top left-hand here, you're going to see one of the simulations that we did, the physical ones. You can see a projectile going in, you can see a lot of fluid going out, but there's actually a small amount of backspatter you can see coming out. That's actually very important knowledge. And what we were trying to do was use SPH to simulate that, and we were trying to validate the models spatially and temporally so that we could reuse them again later. But one of the nice things about these models is that you could do a deep dive and find out more about these underlying effects. And so there you can see the projectile moving through, and actually this cavitation mechanism where it collapses on itself, is actually kind of what produces this back spatter going in the opposite direction. And so forensic scientists spend a lot of time and a lot of money with these physical simulations, and they have blotting paper everywhere trying to capture these spatter patterns. But we were able to kind of produce these things once the model was validated quite rapidly and quite cheaply afterwards. So this work is actually ongoing, but it was a really good application of this SPH method that we've been working on for years. But for those of you who know me, and one of the themes that I've basically been researching for a long time, it's basically of bone adaptation, how our bones respond to the environment, or as we often call it, bone remodeling. And I've had a number of students work with me on this over the years, and this is actually an example that was created by one of my PhD students, Julie Kim, who recently just defended her thesis. And this example is really cool, and I show this to my undergraduate students all the time. And so if you were to take a simple model of your hip, top of your femur, okay, and apply two simple loads, a joint contact force and a muscle reaction force, you can get a stress pattern which kind of tells you where the density in your bone is likely to be highest. But you can also plot these contours, which we call principal components, and these contours, which have zero shear stress, for those of you who do engineering, but it also basically tells us these lines that have the maximum normal stress. You'd expect the underlying structure to line with that so it can resist these external loads. And then when I show the students this is radiograph of someone's femur, not, it could be anyone. They always seem to have this exact same structure. Thick cortical bone, exactly where the model predicts you should have density high. Also, if you look at these structures here, this arch and these longitudinal directions and this longitudinal loading direction, it aligns exactly where we said they would based on these contours of principal stress. And I show this to my students all the time. They're absolutely blown away how I can take a simple geometry, give it a couple of loads, and show you, what this structure is going to be like. And it's because these loadings that I'm using happen to be peak loads from walking, okay, the task that we do most often in life. And our bones are adapted to that. But the cool thing is you can see these effects, which we call, actually Wolff's Law is the phenomenon that we use, in so many really interesting examples. And this is one that I was very, very excited to do with my colleagues in Ningbo, and this was actually work led by one of my previous students, Chi-Chun. We got some rare data on the Chinese-bound foot. Now, this is not something that's practiced anymore, and it obviously doesn't have any health benefits to simulate it, but just the data set alone is such a rare, unique data set that it's really good to showcase the effects of bone remodeling. On the left here, you have a typical foot, and typical geometry, and we load it in a typical way from walking. And our model predicts that you should get this thick region of density behind it, and lo and behold, that's exactly what the CT image shows from that individual, okay? And most people will have a very similar cortical thickness. However, a person with a Chinese-bound foot doesn't load their foot in the same way. In fact, their heel bone, okay, hardly receives any loading. That's rare to come across someone who hasn't really loaded their heel bones throughout life. And what our model predicted based on this geometry and this rare information about the loading pattern is that you should really only get a bit of density occurring right there at the point of contact with other bones. And lo and behold, that's exactly what we saw in this CT image, and pretty much no real cortical density had formed. So it was, such a good example of Wolff's Law in action. And you can see these things going all the way back to early life. And a number of years ago, I was very fortunate to get involved in a study looking at foot development in infants. And this was a very interesting study because we were following infant foot development, which typically occurs when they start to walk around, say, 10 to 12 months, all the way up to 2 years. In that first year of walking, you get amazing changes in bone structure. Okay, if you've ever seen a CT of an infant's foot, in the first year, it almost shows no bones whatsoever. It's because they crawl. Okay, you only get a little bit of bone on your heel. So we followed these families, and that alone was half the challenge because First of all, you had to get the family support because, these infants obviously don't follow instructions. And so you needed the support of the families, and we often had one parent at one side who was encouraging their child onto the platform, and another one at the other end waving them in. And we designed these little infant tight suits because they don't like having markers put on their skin. By the way, I have a whole box of these infant tight suits in my office if anyone's interested. Take them off my hand. And what we were doing was, we were taking their unique gait patterns, their unique kinematics, and we had this very rare data set from colleagues overseas and building a finite element foot model of the infant. And on the left here, we actually have what happens when they've basically just started to walk. And when you ever watch an infant first start to walk, they essentially walk on their heels because they have no bones in the front of their feet. And that's exactly what we saw. We saw stress patterns only in the heel of their foot. And when we looked at the prediction of architecture, we got these vertical lines in the rear. And lo and behold, when we looked at some bone sections that had been sampled by another group, that's kind of exactly what we saw. Nothing going at the front of the heel bone. We had these longitudinal lines of structure occurring in the rear. Fast forward 1 year, okay, and what infants do is they start to flex their feet more, or plantar-flex their feet, as the bones in the front start to ossify. And what we predicted was, as a result of that, when an infant flexes, they start to pull on these tendons here, these plantar fascia tendons, and you start to get stresses all around the bone, and you also start to get longitudinal architecture happening here. And lo and behold, if you look at a specimen of bone from that age group, that's what you're starting to see, these longitudinal structures as well as the rear. So it's amazing seeing this development in an infant's foot, and because by the time they get to 2 to 6, a lot of their architecture and their walking patterns have matured. So that first year of life is absolutely key. It also told us in certain people who have conditions, or if you get that delayed development, what you're kind of missing out on in terms of that bone development. And this led me to another area, again, where I was interested in what happens in your feet. I sometimes call it rather controversial topic of barefoot running. Now, for those of you who have heard about this, you've probably seen shoes in stores that kind of look like foot gloves. Around about 2004, there was an evolutionary biologist named as Dan Lieberman who published this Nature paper called Born to Run. And in it, he proposed that maybe we should run more like our ancestors do, who ran barefoot. And sometimes they landed on the forefront when they run. And of course, there's been a lot of research in this area over the years, but the one that hadn't been done too much was actually looking at the shape of your feet, believe it or not. So we actually got a big population of people, those people who've worn shoes most of their life, and they tended to have feet shaped like that, where the front of your foot is more constrained, versus those people who are more naturally barefoot. They've really never worn shoes most of their life, or open-toed sandals. You'll notice there's a big space, or what we call a hallux, between that big toe and the rest of your toes. And we were wondering whether, this foot shape, which, you've been getting from birth, might have an effect on your running pattern and the kind of stresses that you would experience. So what we did was we got them to take their shoes off and run over a pressure platform. And this is what we saw. Okay, those people who typically had worn shoes all their life, or what we call shod, they tended to have a stress pattern like this when they ran. They tended to land more on their heels, as you do. We all used to running heel strike first. And on the ball of your foot, as you push off, you tended to get more stress on your big toe and on the ball of your foot, but more on your medial side. Whereas those people who've been barefoot all their life, they tended to load their heels much less, but they tended to land more mid and forefoot. But more importantly, the pressure pattern was a lot more evenly distributed around their forefoot. So their toes, which in this case were experiencing almost nothing, were now experiencing load, and this pressure pattern was more central. And so what we suggested was that people who, for example, have been shod all their life, and all of a sudden decide to run barefoot and take the forefoot strike running pattern, which goes with this style, all of a sudden they're going to be experiencing this loading pattern, which their feet, their muscles and bones had not been experiencing before. And it very likely explains, the high incidence rate that came about when people started to run barefoot, who've been shod all their life. So, it's not just the forefoot or rear foot strike pattern, but very much the shape of your foot, which is something that's pretty hard to change overnight, actually affects the distribution of stresses in your foot and how you're likely to experience them. But not all my work is about health and sports biomechanics. Actually, some of it was about entertainment. And back in about 2011, I was very fortunate to do a project with Weta. And those of you who know Weta, that's one of New Zealand's largest film companies. And so this was work that was led by Masood, who was my second PhD student named Masood, so apparently I just need one more to complete the set. But Kumar was the project leader, and what we found out was that Weta was interested in doing physics-based simulations of muscle contractions to help improve their creature animation. So at the time we thought, well, a good way to get an understanding of the structure was to use MRI, but also to use a sequence that some of you may know of called diffusion tensor imaging. Kind of tells us a little bit about the fiber structure. And what we did was we imaged a whole cohort of people, and we embedded this rich muscle structure that we found into these muscles, and then we simulated muscle contraction. Okay? And when we did it, we were absolutely blown away about how realistic these simulations looked. And we even compared them with the individuals when they were scanned. And I should mention they had a very low adipose tissue, so we could actually see their muscles through their skin. We scanned them when they were actually contracting in an isometric state, and they were very, very similar when we overlapped them to these muscle contractions. So Weta were really excited about it, but actually one of the funny things we found about this particular project was how you validate this workflow. It turns out that you use vegetables. So a couple of trips to the supermarket, and we were coming back with all kinds of long stem veggies. We ended up settling on celery because celery has these long fibers in them, and we built these phantoms that we knew exactly the orientations of them, and then we put them through the whole pipeline to try and predict what orientation those fibers were, because we knew exactly what they were from this phantom. And we found that on average we could predict it within about 3 to 4 degrees error. So it was pretty good, but in the end, Weta was more interested in these cool animations that we were actually able to produce. So that was a cool project. And I really started to get an interest and passion for underlying structure, because it tells us a lot about form and function. And I was very fortunate to start working with Jill Cornish over in the medical school, who's got a history in bone biology. And this was our PhD student at the time, Darshini. And we were very fortunate to get hold of some bone biopsies that had been retrieved from an actual clinical trial. So very rare data. And these are some micro CT images showing you what they looked. And on the left, you have kind of like a healthy control biopsy. And as you move right, you have osteopenia and then eventually osteoporosis. So you get increasing voids, less struts, the integrity of the bone is compromised, and so it becomes weakened in strength. And what we wanted to do was to try and see if these mechanical measures that we could measure were very similar to the micro CT metrics that they were computing across the road, across the bridge, I should say. So we set about 3D printing them. And we thought, well, we can't destroy the biopsies, but we can destroy these 3D printed models. So we 3D printed them, and we conducted a whole stream of instron tests, compression tests. And we noted exactly where these struts were starting to fail, and also their force elongation curves. And lo and behold, when we simulated these micro FE models, we were quite delighted to see that wherever we had these high stress concentrations, that's pretty much exactly where these micro struts were starting to crack. So we were able to measure and also validate these spatial locations, but we were also able to get a good understanding of its average strength. And one of the nice things about this particular study was that we were actually blinded to everything that was going on across the road. We had no idea what they were measuring in the micro CTs until they opened up the key at the end of the study. And then when we actually measured the strength that we computed from these various biopsies, we were absolutely delighted to show that the trend was quite similar to what had they computed. So it told us that these micro CT measures were also good surrogate measures for the mechanical strength inside these bones. So that was a really, really cool study. But what we found out there was people liked these 3D printed bones that we made, and they started showing up at open days and postgraduate evenings, and somehow they ended up over in the Department of Psychological Medicine in Keith Petrie's group. And Keith does a lot of research that looks at people's perceptions in clinical trials. And they had this really cool idea to say that, what if we showed people what osteoporosis looked like in a 3D printed model? Would that somehow change their knowledge, their understanding, and their likeliness to uptake a treatment? So this was the work of Melika, at the time, Melika. What we did was we 3D printed all these bones. Some of them were healthy, typical developed, some of them were osteoporotic, and we distributed them amongst a bunch of surgeons. And what happened was the surgeons, half the group got the normal communication, and the other group was augmented by also being showed these 3D printed bones. And the amazing outcome was that all the people who were shown the 3D printed bones not only showed a better understanding of their disease and osteoporosis, but they were more likely to undertake an oral bisphonate, which is one of the methods to use to improve your bone density. So that was an amazing outcome. And then Amy came along, and she was quite interested. Well, could we do one better if we had animations of the bones? It's obviously a lot cheaper. And so she kind of redid the study, and one group got the normal message, and the other group got both, one group got 3D printed bones, and another group got these animations. And the outcome of that study showed that both the animations and the 3D printed bones both had the same effect. So they both produced a better understanding, a better motivation, and more likely to undertake bisphosphonate treatment. So the nice message is that some of the cool things we do can actually play a role when clinicians are communicating and informing people about their potential treatments. So this was a really good example. It was also my first foray into psychology studies. And a number of years later, actually when I was in 2019, when I was having research and study leave, I was starting to think about ADHD, and in particular its links with biomechanics. Because the literature was saying that people with ADHD have different gait. They sway differently, they have a different posture, they walk with different speeds. And I was like, well, these are gross motor skills. What about some of the finer motor skills like fidgeting that is often presented with people of ADHD? And I started talking with Karen from the School of Psychology, and we started to hash out these ideas. And what we wanted to do was to see, for the first time, what happens if we put someone in an MRI, get them to do a higher executive functioning task with the aim of eliciting this executive function, and find out if fidgeting actually interacts. And the great thing about this project is I started working with this very multidisciplinary team of people. We had psychologists, psychiatrists, technicians, engineers, people from industry, all came together thinking that this potentially could be a new biomarker. What we did was we got someone to lay in an MRI, we isolated their legs so their movement would not affect any brain artifact, and we got them to look at these arrows and they would choose these paddles, seeing if it was left or right. It didn't matter if they got it right or wrong. What was important was that they were thinking and not dreaming or sleeping. Because when you do that, you elicit this activation or oxygenated blood in the front lobes of your brain. And what we saw was, on average, people who were neurotypical had this increased activation, which is what you'd expect. But we also saw that people who had ADHD had underactivation. Now, this was an exciting result, but people had seen it before. In fact, Karen saw it 20 years ago when she saw this. But the different thing we did this time was we then asked them to do the same thing while fidgeting. And what we found was that those people who were neurotypical suddenly had reduced activation in the front lobes of their brain, whereas those people with ADHD generally tended to have increased activation, almost as if it had been normalized to what the neurotypical is. It appears that fidgeting was distracting for people who are more neurotypical, whereas for people with ADHD, it was a very chosen strategy that they'd used to somehow increase this activation. It's almost as if they were fidgeting with a purpose. And it was nice because a couple of years ago they did a New Zealand listener article on what we found, and they actually talked to psychologists in other parts of the world, not just New Zealand, and they found that what we were finding fit very nicely with some theories that they had, but this was the first time that anyone had ever measured it. So we were really excited about that. So I'm going to bring this to a close. I just want to thank all these funders who've made all the work we've done possible over the last 10 to 13 years. Without their support, a lot of this work would have just ended up being small pilot projects and stopped there. And I was thinking about this. As I look forward to what's coming next, I realized that inevitably I'm going to come across more unexpected adventures. And as I look behind from my own experience, I realize the best outcomes have always come from when I've collaborated with multidisciplinary, talented, and very diverse groups of people. So as I look forward again, I realize that I'm going to have to ask you all for help. So I really want to acknowledge, people that I work with every day. Big shout out to all the professional staff, who really make a lot of our projects smooth and just work so well. People who I work with overseas, and institutions like Matai, and I look forward to working with you all again. Thank you very much for sharing this day with me. Tēnā koutou, tēnā koutou, tēnā koutou katoa. Thank you.